Alright guys, going to help you out with some of your work here. Some people said they were having problems. So A and B, you can get that from the notes if you watch the notecast. But I'll start helping you with 2A. Alright, so for 2A, it tells you to react this with water. So let me try that again. So we're going to react it with water, right? So identify is with acid or base. So this says it's an acid right here. So acids, remember, donate hydrogen ions. So if this is the acid, right? So if this is an acid, that makes water base. Water is amphoteric, and amphoteric means it acts as either an acid or a base depending on what it's with. All right, so what's going to happen is this is going to transfer a hydrogen ion, right? So that's the way we do it. We'll go like this. So I'll take a hydrogen away from there. I'll have bisulfate, and since I took a positive charge away, it has a resulting negative charge. And that hydrogen, remember, went to water, so now it's hydronium. And that positive charge now is over there. Okay? So that's how we do it. All right, so if I look at both a base, potassium hydroxide is a base. So remember, water is amphoteric. It'll react with whatever it needs. Now, here we have a situation where potassium is a spectator. Screen, it's a spectator. So I can ignore that in the equation. Right? So for this one, this is my base. This is my acid. And my hydrogen is going to go that way. Okay? All right, so what we're going to have here is we're going to have we're going to end up with what exactly we started with. Now potassium, since it's a spectator, I can get rid of that because it's going to simply be an aqueous solution, right? So I end up with the same thing I had before. All right. So you can do the same thing. Perchloric acid, that's going to be an acid, so that's going to be like A. Ammonia, so let me write this right here. So ammonia, remember, is NH3. But remember, it has an extra pair of electrons here. So ammonia is going to be a Lewis base. Okay, so D, you're going to do like C. And E is an acid, and it's going to be like A. So you should be able to do all those now. All right. So for number 3, it tells you to find the conjugate acid-base pairs. So same thing. This leads with H, so we know that's an acid. All right, so this is an acid. That would make water a base. All right. So my acid, what we do is go like this. So when it loses that hydrogen, it becomes NO2. So this is my conjugate base, right? And my base accepts the hydrogen. So this would be my conjugate acid. It's okay if you use that Ca for me. Okay, so my base makes a conjugate acid, my acid makes a conjugate base. All right, same thing. So if you look at B, right? So we have ammonia again. Remember I said ammonia because it has those 2 extra electrons. It's a Lewis base, which would make water my acid. Right? So do it the same as the top, and then the bottom you should be able to do as well. So that should help you out with that. All right. So number 4, you're going to do just like above. You're going to identify the acids and bases. So we have a problem here. So we have both of these with hydrogens. So now we have to look at it and look at these extra electrons here, right? So since that's an anion, right? So that would be a Bronsted-Lowry base, right? Because it can accept a proton. This does not have one, right? So bicarbonate is going to be your base. So this is going to be your base, right? And you should be able to figure it out from there. Okay. So same sort of thing as above. All right. So Ka here, right? So the concentration of the acid is your Ka, right? So we have different concentrations here. So the following is a list of weak acids and their concentrations or their Kas. 3.5 times 10 to the 8, 1.1 times 10 to the negative 7, 4.0 times 10 to the negative 10, and 4.5 times 10 to the negative 4. So we can figure out the pHs of these, but remember that pH is rationalization of the exponent, sorry. So rationalization of the exponent, right? So 10 to the negative 4 would be a pH of 4, but since I have a number greater than that, right? So this is less than 4, because it's going to be between 3 and 4, right? So this is less than 10, less than 7, and less than 8. Right, so this is where we estimate those. If we were actually going to do the pH, I'll pause it and I'll do the actual pHs for you. You see when I use the negative log of a hydronium ion, if I use this equation right here, right, I start to get these numbers. So for the first one right there, when I plugged that in, I said it was going to be less than 8, and it's 7.4. The next one would round to 7, right? 6.96, and then I get 9.4. So estimation, I use estimation like I did right here, right, to estimate it. So which is strongest? Remember, if we have the pH scale goes from 0 to 14. Right? So the strongest acid would be closest to 0. So whichever of those is closest to 0, because it has the highest concentration. The Ka expression of the strongest acid, essentially what I wrote up there. Which acid has the strongest conjugate base? Okay, remember, a strong acid has a weak and a weak acid has a strong conjugate base. Right, so those things are both true. So now you should be able to estimate and give your right answer. Okay. So if you start to look at number 6, right, calculate the concentration of hydroxide ion in a sample of seawater, or the concentration in a sample is 5.0 times 10 to the negative 6. Calculate the concentration of hydronium ions. All right. Remember, if we have, because the dissociation constant of water right? Well, let me erase that because it's hard to see. Right? So the water dissociation, or Kw, right? The product of that, H0 times OH is 1 times 10 to the negative 14. So if we substitute this in, all right, so we could substitute this in to there. So we would have the equation like this. The concentration of hydronium is equal to 1 times 10 to the negative 14 divided by 5.0 times 10 to the negative 6. Right? If we rearrange that formula, we would get that. So that's how you solve that. Right? And you would do the same way on the next one. And then you would figure out the pH to find out if it's acidic, neutral, or basic. Right? So if we go to number 8 now, and 8's at the end of it. For each of the following, determine the hydronium and hydroxide concentration where it's at. So essentially you're doing the same thing. The difference is, molar, so since it's an acid, we're looking at the concentration of hydronium, and you simply have to put this into scientific notation. All right, so it's 1.5 times 10 to negative 2. So that's my concentration of H3O. All right? So from that you have to figure out the OH, right? And then you have to figure out what the acidic, basic, and neutral. All right, so remember this is molar concentration. So in this one, you have to make this into moles. So for this, right? Right, so we have to figure out moles. I'm going to move this over a little bit so I can finish talking to you. Right? And then we have to change that. Actually, I'll just move it up here. So this will give you mole, and then we have to go to molarity, which is moles over liters. So you're going to have to change this into liters and put it down there. And once you do that, you can do it the same way as the other one. All right, well, I hope that helps everybody out. Good luck if you still have AP exams to take this week, and I'll talk to you later. Bye.